Our last speaker today is Tristan Benoist. He's currently a researcher at Toulouse Mathematics Institute. Today he will talk about deviation bounds and concentration inequalities for quantum noises. Tristan, please.
I hope you can see my slides and it's full screen.
Yes.
There's no issue.
Yes.
Okay. So thank you for accepting us to present our work. So it's a joint work with Cambyse Rouzé, who just talked. Lisa Hänggli are both in Munich. So I will talk about something like we try to relate some like all the functional inequalities you heard about before, to try to find some statistical meaning to them and to derive some deviation bounds. So just I'll just start with the classical introduction to this problem. So typically, like the most simple classical probabilistic setup I can think of such concerns is what I would be talking about. It's just you take a finite state space, you have a probability measure on the state space, and your goal is to estimate this probability measure. So you have one solution to it, that if you have an ID sample of the distribution, so you can just take the empirical average and empirical measure, and it will give you an estimator of your measure. But sometimes, of course, you don't have access to a sample of your probability distribution. So you need you only have access to some Markov process with the generator L here, and the measure you want to estimate is the invariant measure. I will assume always here that it's unique and cyclical. Another estimator is just taking an empirical average of the time, like the local time of your process, of your Markov process. So still, the Markov process is still on the finite state space. So what kind of results we have? So we have two deviation bounds here, maybe more like actually large deviation principles. In the IID case, we have Sanoff theorem that just tells us that, okay, if we are far from the invariant measure, it will decay like, sorry, it should be a pi here at the end. It will decay like, given the relative entropy between the target measure and the one you are deviating from. And if you take the process, so E of t, so if you have a Markov process, actually what the rate will be given by another quantity that depends on the generator here. This is thanks to Don's covariance theory. You can go a bit further when you have like what is called reversible Markov chains. So in the physics community, the reversible Markov chains are known as satisfying what is called a detailed balance condition, which is an equilibrium condition. And so that essentially says that your Markov generator is said to verify development if it's self-adjoint with respect to an inner product, like a weighted inner product on your functions of your state space, and the weight is given by the invariant measure. And like for physicists, it's more often that they see this formulation here of detailed balance, that you are as likely to start from a point and going to another one than to do the opposite jump. And so this is why it's called also reversibility. The chain itself is reversible. To express the deviation bounds, we use what's called the Dirichlet form. So it's just it's defined like that. So using the generator and the inner product that defines the detailed balance condition. So typically, when it's reversible, this is related, of course, when L is symmetric. So this will be will inform you about the spectrum of L, and so that's what we will use to derive some bounds. So we have when we have the detailed balance condition, we have results from Dushan in Strouk in 2001 that tells you that essentially you can, the rate function we had here before for the Markov chain is actually related to this Dirichlet form, with A here as the square root of the Radon-Nikodym derivative. And so basically that for any function, measurable function, and any initial distribution. So we have large deviation principle, but with here as a rate function that is expressed using the Dirichlet form. So that I want to highlight the fact that here in the expression of the rate function, so we take any distribution such that the average is equal to x of f with respect to this measure is x, and we look at the value of the Dirichlet form on for this measure. This is how you get the so to be completely rigorous, you need to take a regularization of this function and you get your rate function. Using this formulation, you can also actually use some functional inequalities to derive some concentration bounds. And so for first you have like the logarithmic Sobolev inequalities that will tell you something here. That if you have a log Sobolev inequality, what it tells you is that your average with IAD samples will have a rate of convergence that is upper bounded by 1 over alpha of the Dirichlet form. And the maximal alpha such that you have this inequality is what's called logarithmic Sobolev constant. So this is, you can interpret, the point is that you can interpret both sides of this inequality depending on different stochastic properties. The one that will be maybe a bit more interesting is transportation information inequality. So that, again, is for any measure that is absolutely continuous with respect to a divine measure. You have a constant such that you have this inequality. So the valence time distance, Cambyse already talked about it, so I won't detail it here, because for the classical case, it's always the same. You just depend on the distance you define, metric you define on your space, and the Dirichlet form here. So it's standard result now that if you have such an inequality with constant c, then for any Lipschitz function, you have a concentration bound that is Gaussian. So, and so you see that here the concentration bound, so it's Gaussian in the distance with the average. It depends, of course, there is a prefactor that depends on, on the Radon-Nikodym derivative between your invariant measure and the initial measure. But what is more important is that in the denominator of your rate of decay of your probability is a function that is that the norm, the Lipschitz norm of your function. And also, I want to highlight that what is interesting in this inequality compared to this limit is that here you have inequality for every time. So it's a fixed time, finite time result. So this is a classical setting. Now we want to adapt and see what we can do with all that in the quantum setting. So we'll work with Hilbert space in finite dimension. So I would say at the end, like most of our results, upper bound can be generalized to infinite dimension, but let me stick with finite dimension for my talk. So we have some density operators that are density matrices here that will be just equivalent of the probability distribution. And what we want to do is to estimate signal. So of course we could do IAD tomography of our state, but it's not what we want to test here. What we want to see is what kind of actual estimators they can have in experiments. And so we go back, we can look at what they do in experiments, and what they do in experiments is typically this setting. So this is a picture taken from Benjamin Huard's group in Lyon. So what they have is that in the cavity, they have a qubit that is isolated from the outside, and just that sends some electromagnetic field, coherent electromagnetic field, to interact with the qubit, to modelize, to manipulate it, to measure it, and to do some action on it. And of course, the qubit is connected a bit to the environment, because you cannot avoid that, as Oliver told us. So what they obtain is, at the end, some signal, a continuous time signal that comes out of the cavity once the electromagnetic field has interacted with the qubit. So what we will use to estimate, and this is what they use to estimate the state here, you see, of the qubit in the cavity. So what we will use is to construct some estimators of the state inside the cavity, so of sigma, using these signals here. So first, we will start in the same setting as in the classical case. So we will assume that the dynamic of the qubit is actually Markov. So it's modelized by a semi-group of unital completely positive maps. I'm working in the Heisenberg picture here because it will be easier that way. And so, as most of you know, but just to fix notations here from the GKSL theorem, if you have a semi-group of unital completely positive maps, its generator has a particular form, that you have an Hamiltonian, and you have some Krauss operators that I just encode here to take into account the liberty of choosing the different Krauss decomposition directly in the notation. So this is just instead of a sum, I just write L as a map from V of H to a larger linear space. And we'll assume also that our semi group is always primitive. So as before, like just saying that it's primitive, that there is a unique, strictly positive definite density matrix that is invariant in the dynamics. So in Heisenberg picture, it's encoded like that. So from now on, I will always assume that E should be here. Okay, so now I will ask you to trust me a bit on some elements, because I won't be able to give all the definitions precisely and to prove everything about the existence of objects. But let me tell you that there exists a Markov process, rho t, that takes values in density matrices that we call quantum trajectories, as Cambyse told you, such that in average, actually, when you take the average of the Markov process, you recover the semi-group evolution, the quantum semi-group evolution. And also, for any, there exists, like unit vector in CK, so that the signal I mentioned before that you obtain in the experiments is just written like that. So it's xt of u, so it's kind of a time average of what would be an observable here, O of u, that I will relate to L and just afterwards, and the state of the system at time s, plus some noise, and this part will become very important afterwards. The observable here is not any observable, it's just a linear combination, this kind of linear combination of my Krauss operators that were defined here. I cannot use any observable. I need to use observables that I can express that way, can generalize it to something with Poisson process, but I won't discuss that. I will restrict myself for now to diffusions. So there is many different derivation of such a process, and the fact that these processes exist. But in the paper I mentioned that was in the title, we use quantum stochastic calculus because it's somehow the most natural for us. Just a remark now that we have, so we use xt as an estimator of the states, but as you can see, like here actually rho t is Markov, but not the estimator. So we don't have directly, we cannot apply the classical results to xt. We could apply it to the joint process ρt and xt, but the issue is that then the generator is quite difficult to handle, and so we want something that depends only on the Limblad, so the generator of the quantum Markov solution. And why do we know that this xt here will be a nice estimator? Is because we have a law of large number that was proven in 2004 by Hans Maassen and Richard Krummerer. That almost surely, if I take the average of xt, I get the average of O of u in the state sigma, so the invariant state of my solution. So now we want to recover if we can have some results that we had in the classical case. So first of all, I just mentioned it that in there exists, of course, an equivalent of Sanoff's theorem for ID estimation of sigma, and the rate is just relative entropy, quantum relative entropy. You can see it also as some Stein exponent for hypothesis testing. And you also have an equivalent of Donsker-Varadon theorem for the signal. So it's not exactly in this paper of Jakzik Pilevestrich, but actually it's equivalent. There exists a good rate function such that you have a full large deviation principle. So we have a rate function. One of the issues we have here is that the rate function doesn't have a nice expression as we have for in the classical case. It's obtained through a Legendre transform of some Cumulent generating function. So one of the questions we had that if we can relate this rate function to a non-commutative version of Dirichlet form. And for that, we need, of course, notion of like a definition of Dirichlet form. And so we need an inner product, and we will work with KMS inner product here. So this is, most of you must have already seen this expression. So it's just a generalization, one of the generalization of the inner product, classical inner product. And we define Dirichlet form as in the classical case. And here we will take a symmetrized version because we will have some results that do not require the process to be, the generator to be symmetric with respect to KMS inner product. So we have our first result without further assumptions. So we have some quantity that it's not exactly that, but you can see see A as encoding some modification like a generalization of Radon-Nikodym square root of Radon-Nikodym derivative. And this function fu of A is not exactly that, but you can see it as the expectation of O of u with respect to a different state that is given by A. And then for any time and any deviation from the average, we have a finite time upper bound, exponential upper bound on the probability to deviate from that's 1 over t xt of u deviate from the mean. And the rate of deviation is given by an infimum involving the value of the Dirichlet form, but this time we don't have the fact that A, that you can see as a Radon-Nikodym derivative, defines a measure such that the average is equal to the expected average plus the deviation, but actually we have a quadratic term, penalization term. And this quadratic penalization term comes from the fact that we have this Brownian motion on top of the average, the running average. So the proof is based on quantum stochastic calculus, some Markov inequalities. The main original two may be Ando-Gibb concavity theorem and minimax theorem. So now we can go to be a bit further to see what we can obtain for symmetric reversible quantum Markov semigroup. So we say that quantum Markov semigroup is, it verifies KMS quantum detail balance if its generator or the semigroup itself is symmetric with respect to KMS inner product I just defined. So we know from these two papers that if we have a generator that verifies KMS quantum detail balance, then there exists a unit vector in CK such that the map phi u I defined just here is also symmetric with respect to KMS inner product. So if we have that, so we have KMS quantum detail balance, and the u we chose to define x of u is actually such that phi of u is KMS symmetric, then we have that the rate function for the large deviation principle that was obtained in 2014 can be expressed as infinimum over so the generalization of Radon-Koenig derivatives involving the Dirichlet form and a quadratic penalization term. So we have saturation of the bound we have. So we cannot obtain a better bound than what we already have. So now we want to of course, so we are happy with that because it's just a new expression of the rate function, which is like a bit more tractable maybe in some cases than the one we had before. And of course, only for symmetric KMS quantum detail, but now we want to use what Cambyse talked to you about, so like functional inequalities, and to obtain some concentration. But first, we need a finer, more restrictive notion of detail balance, which is the GNS quantum detail balance. So mostly like what people talk about before was about GNS quantum detail balance. So GNS quantum detail balance is verified by the generator if it's symmetric with respect to this inner product. That is a different generalization of the classical inner product. We have some relationship between the two. It was proved first by Fanula and Amitai in 2010, I think, that GNS quantum detail balance implies KMS quantum detail balance. But it was proved also afterwards that the opposite is not true. So we have an example, Carnan and Mass have another one. But okay, GNS quantum detail balance group are still quite interesting because, for example, polarizing channel or Davis generators verify quantum detail balance. So we also have another notion of quantum detail balance that some of you may be interested in, that we have that the GNS quantum detail balance implies PKM quantum detail balance, but not the opposite. Again, there is an example of Carlin and Mass that shows that. However, KMS and PKM notions are not comparable, and we have an example in the paper that we just that was posted in the archive yesterday. So now we have generalization, like as already mentioned, we have a quantum generalization of logarithmic Sobolev inequality and transformation cost inequality. But first, logarithmic Sobolev inequality is the same as the classical one, but just with the appropriate objects. The main point that is useful here and that's new here, that actually now we have an interpretation of the right-hand side of this inequality. So we have a step. So if you remember, this is related, the left-hand side is related to the IID estimation of the state rho. But now we also have a statistical interpretation of the left-hand side here, which is a Dirichlet form, from a statistical point of view, which comes up from quantum trajectories. Now, to obtain a concentration bound, we will use the transportation cost information inequality, as mentioned by Cambyse. So yeah, it's just the same thing in the classical case, using just non-commutative generalizations. But what is more important here is that the Wasserstein distance we have here is not the same one as Cambyse mentioned. It depends a lot actually on the choice of Lindblad generator, on the Lindblad generator we have. And to be able to define it, we require some GNS quantum detail balance because it's how we can define some geometry on our states that's suited for this inequality. Now, using this transportation cost information inequality, then we can obtain also a concentration bound as we had before, like almost the same. So we have, then for any, we do not require that U is such that psi of U verifies the transportation cost KMS symmetry. But what we have is that so we have deviation from the mean that is upper bounded by a constant and an exponential that is quadratic in the deviation. And the denominator is the same as in the classical case, except that the Lipschitz norm is not directly the Lipschitz norm of the operator O of U, so of the of the observable or the function, if you like, but you have these terms like this, the invariant state that comes up in the definition of this norm. So as Cambyse mentioned, that is a bit different, and there is a question if we can get rid of it. But actually, this is like typically a quantum setting because these terms, if you take like you can parallel all the formalism, the quantum formalism and the classical formalism, and these objects here come from the modular operator that does not exist in classical probability, but exists in quantum setting. Again, the Lipschitz norm here depends on the Limblad generator and requires GNS-KDB for its definition. So to conclude rapidly, that we have actually a bit more than what I just talked about. So we can deal actually with multidimensional diffusions. We have also some similar results, including Poisson processes for the signal xt. We don't have the concentration bounds, but we have some expression of the rate function and the upper bound using the Dirichlet form. So the upper, all the proofs actually, most of the proof, at least the upper bounds, should still hold for H infinity dimensional under some appropriate assumptions, so existence of a faithful invariant state and like threshold state and things like that. We didn't do it yet because it's just a technical generalization. And also our proofs are based on a non-commutative extension of stochastic calculus and Girsanov transformation. However, we can actually do everything using classical stochastic calculus, commutative stochastic calculus. However, it's harder to because we use at one point a deformed generator, and it's harder to derive the deformed generator in classical stochastic calculus, and it's easier to do it in quantum stochastic calculus. Thank you.
Thank you, Tristan, for this very interesting talk. Is there any questions from the audience? Okay, I have a question. So in your main result, you need an assumption of that the transport cost information inequality holds with a positive constant. So I think that this is the...
This one?
Yes. So
yes.
Do you have any ideas how to verify this or how to prove this?
So we have some examples where, sorry. Yeah. So we have some examples where we can, sorry?
No, please go ahead.
Can you kindly repeat the question because it was too soft?
Okay, so here the main result requires an assumption that the transportation cost information inequality holds with a positive constant. So my question is that how to verify this condition?
So I must say I'm not an expert in this transportation cost in information inequality, and as I told Cambyse, I would redirect questions to him. But we have some examples where this holds actually, like this inequality holds. But I'm not expert. I mean, I'm more expert on the stochastic part of things here, and so I know there is some examples, but I wouldn't be the best person to ask about that. Okay. That when, what are the examples where it works?
Okay. Any other questions from the audience? We can move on to the Slack channel for further discussions later. So let me thank all the speakers and session chairs. And all the speakers, please send your slides to to the organizers, beyondid9@gmail.com. So I can post your slides on the website later. Okay, thank you very much.
Just, yeah, Cambyse reply to your question, like you can prove it for tensor product or of depolarizing or the Gibbs sampler, like Angela mentioned.
Or such examples. Okay, thank you.
Thank you.
Okay, then we'll see you tomorrow. Bye.